Next lesson is about discretization method, control volume approach. Often, elementary textbooks on heat transfer derive the finite difference equation via the Taylor series methods and then demonstrate that the resulting equation is consistent with the heat balance over the small region surrounding a grid point. We have also seen that control volume formulation can be regarded as a special version of the method of weighted residuals. The basic idea of the control volume formulation is easy to understand and lends itself to direct physical interpretation. The calculation domain is divided into a number of non-overlapping control volumes, such that there is one control volume surrounding each grid point. The differential equation is integration over each control volume. Piecewise profiles expressing the variation of phi between the grid points are used to evaluate the required integrals. The result is the discretization equation containing the values of phi for a group of grid points. The discretization equation obtained in this manner expresses the conservation principle of phi for the finite volume control volume, just as the differential equation expresses it for an infinitesimal control volume. The most attractive feature of the control volume formulation is that the resulting solution would imply that the integral conservation of quantities such as mass, momentum and energy is exactly satisfied over any group of control volumes and, of course, over the whole calculation domain. This characteristic exists for any number of grid points, not just a limiting sense when the number of grid points becomes large. Thus, even the coarse grid solution exhibits exact integral balances. When the discretization equations are solved to obtain the grid point values of dependent variable, the result can be viewed in two different ways. In the finite element method and in most weighted residual methods, the assumed variation of phi, consisting of the grid points values and the interpolation functions between the grid points, is taken as the approximation solution. In the finite difference method, however, only the grid point values of phi are considered to constitute the solution. About any explicit reference as to how phi varies between the grid points. Without any explicit reference as to how the phi varies between the grid points. This is akin to a laboratory experiment where the distribution of a quantity is obtained in terms of measured values at some discrete location, without any statement about the variation between these locations. In our control volume approach, we shall also adopt this view. We shall seek the solution in the form of the grid point values only. The interpolation formulas or the profiles will be regarded as auxiliary relations needed to evaluate the required integrals in the formulation. Once the discretization equations are derived, the profiled assumption can be forgotten. The viewpoint permits complete freedom of choice in employing, if we wish, different profile assumptions for integrating different terms in the differential equation. To make the foregoing discussion more concrete, we shall now derive the control volume discretization equation for a simple situation. Let us consider steady one-dimensional heat conduction governed by the following equation. d by x of lambda dt by dx plus s is equal to 0. Here lambda is the thermal conductivity, T is the temperature, and S is the rate of heat generation per unit volume. To derive the discretization equation, we shall employ the grid point cluster shown on this figure, figure 2.2. We focus attention on the grid point P, which has the grid points E and W as its neighbors. E denotes the east side, so the positive x direction, while W stands for the west or negative x direction. The dashed lines show the faces of the control volume. Their exact location are unimportant for the time being. Letters, small letters E and Y, denote these faces. For the one-dimensional problem under consideration, we shall assume a unit thickness of in the y and z directions. Thus, the volume of the control volume shown is delta x multiplied by 1 multiplied by 1. If we integrate equation 2.13 over the control volume, we get the following equation. Lambda dt by dx at E point minus lambda dt by dx w plus integral of s dx is equal to 0. Profile assumption. To make further progress, we need a profile assumption or an interpolation formula. Two simple profile assumptions are shown in figure 2.3. The simplest possibility is to assume that the value of T at the grid point prevails over the control volume surrounding it. This gives the stepwise profile sketched in figure 2.3a. For this profile, the slope dt by dx is not defined at the control volume faces, at V, at W and OE. A profile that does not suffer from this difficulty is the piecewise-linear profile, which is shown on figure 2.3b. Here, linear interpolation functions are used between the grid points. the discretization equation. If we evaluate the derivative dt by dx in equation 2.14 from the piecewise linear profile, the result of the equation will be the following: lambda e t e minus tp over dx e minus lambda w tp minus tw over dxw plus s dx is equal to 0. Here S is the average value of source of the control volume. Treatment of the source term. Let's give some attention to the source term S in equation 2.13. Often the source term is a function of the dependent variable t itself, and it is then desirable to acknowledge this dependence in constructing the discretization equation. We can, however, formally account for only a linear dependence because, as we shall see later, the discretization equations will be solved by the techniques for linear algebraic equations. The procedure for linearization of given dependence S of t relationship will be discussed in the next lessons. Here it is sufficient to express the average value of S as the following formula. Average value of S is equal to SC plus SP TP, where SC stands for the constant part of S, while SP is the coefficient of TP. It is obviously that SP does not stand for the S evaluated at the point P. The appearance of TP in equation 2.16 reveals that in expressing the average value S, we have presumed that the value Tp prevails over the control volume. In other words, the stepwise profile shown in figure 3.3a has been used. With the linearized source expression, the discretization equation will be the following: AP TP is equal to AE TE plus AW TW plus B, where AP is equal to EIE plus AW minus SPH, and coefficient AE is equal to lambda E over dxe. AW is equal lambda W over dxw, and the last b is equal to sc delta x. In general, it is convenient to think of equation 2.17 as having the form, as you see in this equation, APTP equals sum of A and B, T and B, plus B, where the subscript NB denotes a neighbor, and the summation is to be taken over all the neighbors of point